Welcome to Daily Papers, the podcast where we break down the latest research into bite-sized conversations. Today we're talking about the AI arms race.
It really does feel like an arms race, doesn't it? Every few months, we hear about a new AI model that is bigger, more complex, and more powerful than the last. It's this mantra of bigger is always better.
But what's the cost of bigger? A paper from researchers at UC Berkeley challenges this whole idea. It's titled, AI Progress Should Be Measured by Capability Per Resource, Not Scale Alone.
Right. They kick things off with a pretty staggering statistic. Training just one famous large language model, GPT-3, produced 552 tons of CO2 equivalent. That's like a round-trip flight from London to New York for about 300 people.
And for what? The paper points out that these massive models often show diminishing returns. You pour in vast amounts of extra energy for a tiny improvement in performance. It's like using a sledgehammer to crack a nut.
The authors call this mindset scaling fundamentalism. It's the belief that the only way to make progress in AI is to just keep scaling up. More data, more computing power, bigger models. It's a bit like the early days of muscle cars. The solution to everything was just put a bigger engine in it. It works for a while, but you end up with a car that's incredibly powerful, but also incredibly wasteful and inefficient. You're ignoring things like aerodynamics, weight, or fuel efficiency.
And this scaling fundamentalism has two big problems. First, the environmental costs we just mentioned. Second, it creates a huge divide. Only a handful of giant, well-resourced tech companies can afford to play this game. The paper says this is creating computational oligarchs who dictate the direction of AI for everyone.
So this paper asks a simple but profound question. What if we stopped trying to build a bigger engine and instead tried to build a smarter, more efficient one?
Exactly. Their core insight is something we can all relate to, the 80-20 rule. You know, the idea that 80% of the results often come from 20% of the effort. They found the same thing is true inside these massive AI models.
To understand this, we need to quickly define two terms. First, parameters. You can think of these as the billions of tiny digital knobs or dials inside an AI model's brain. During training, the AI learns by adjusting these knobs.
Second, gradients. A gradient is basically a learning signal. It tells the AI which direction to turn each of those knobs to get a little smarter at its task. A strong gradient means, turn this knob, it's really important. A weak one means, this knob doesn't matter much right now.
And what the researchers found is that in these giant models, a very small fraction of the parameters get most of the strong gradient signals. A tiny percentage of the knobs are doing almost all of the important learning.
So instead of spending massive resources to tune all 100 billion knobs, what if you just focused on the 10 or 20% that are actually doing the heavy lifting? The paper shows this is dramatically more efficient. You get almost the same performance for a fraction of the cost.
And it's not just the model's parameters. The same rule applies to the training data. Not all information is equally created. Some pieces of data teach the model way more than others. So you can also be selective about the data you use, focusing on the most impactful examples.
Okay, so that's the theory. Focus on the important parts. But how do you know which parts are the important ones in a model with billions of parameters?
This is my favorite part of the paper. They propose a new tool called a gradient blueprint.
A gradient blueprint? It sounds like a schematic for an AI's brain.
That's exactly what it is. The idea is that when a big company builds one of these massive foundation models, they shouldn't just release the model itself. They should also release this blueprint, a small file that acts as a treasure map.
So the map would say things like, for tasks involving understanding English, the knobs and layers 10 through 15 are the most important. Or if you want this model to be good at writing code, focus your energy on these specific attention blocks.
Precisely. This blueprint tells everyone else which parts of the model matter most for different tasks. It takes the guesswork out of it.
And this creates a new two-stage system. In stage one, the big labs do what they do best. They pre-train the massive model. But crucially, they stop training when the performance gains start to flatline, saving wasted energy. And they create the blueprint.
Then comes stage two. A university researcher or a small startup wants to adopt this model for a specific task, like analyzing medical texts. In the old world, they need a supercomputer to fine-tune the entire model, but now they can just use the gradient blueprint.
They look at the map, see which 10% of the parameters are most important for their kind of task, and they only train those. Suddenly, a task that was impossibly expensive is now doable on a much smaller budget. It democratizes access to cutting-edge AI. And here's the real kicker. The paper shows that these efficiency gains don't just add up, they multiply.
What do you mean by multiply?
Well, say you make the model more efficient by only training 20% of its parameters, and you make the data processing more efficient by only using the 30% most useful data examples. The paper gives an example where combining these two strategies gives you 72% of the total possible performance improvement, but at only 6% of the original resource cost.
Wow, that's a 12 times improvement in performance per resource. That's not a small tweak. That's a fundamental shift in how you approach the problem.
It completely reframes the conversation. Methods that people used to think of as hacks or workarounds for people who couldn't afford powerful computers are in fact the theoretically smarter and more optimal way to do things. Being efficient isn't a compromise, it's just better science.
So this paper is really a call to action. It's arguing that the entire AI community needs to change how it measures success. The key metric shouldn't just be capability, but capability per resource. How good is the AI relative to the energy it took to create?
It's a push towards a more sustainable, more equitable, and honestly, a more clever future for artificial intelligence. It argues we can have continued progress without the ever-growing environmental and financial costs.
So the next time a company announces a mind-bogglingly huge new AI, the question we should be asking isn't just what can it do, but also how efficiently was it built? A very different way to look at progress.